Hello everyone, I'm J Wildberger. Today we're going to be continuing with our Sociology and Pure Mathematics series, where I'm trying to have a larger look at the sociology of pure mathematics and what's really going on there in terms of underlying assumptions and actually the logical integrity of the subject. I think there are really serious issues that the professoriat is working hard not to look at. So today we're going to be looking at 5 challenges in the direction of whether the subject is actually logically viable. So more or less, pure mathematics is regarded by most people as sort of the apex of logical correctness and clarity and rigor. But is this really justified? In my view, pure mathematics is actually almost a belief system. It's a belief system, unfortunately, resting on very dubious foundational assumptions and definitions. And today I want to illustrate that in a very direct way by giving my colleagues 5 very explicit, concrete challenges that shed light on the very significant weaknesses currently besetting the subject. So our first challenge will not be a surprise to the regular listeners to my channel. It's a challenge that I've presented on many occasions and probably will still have to, okay? And for some curious reason, no one seems to be able to adequately meet this challenge. Okay, what is it? Well, it's to simply calculate the sum of arguably the 3 most common irrational numbers, which are pi, e, and square root of 2. So in the usual story, analysis is built up from so-called real numbers and their arithmetic. These are arguably the simplest or most common real numbers which are not rational numbers. Arithmetic consists of various operations, but addition is the simplest one. So let's apply the simplest operation to the 3 arguably simplest irrational numbers. What do you get when you do that? What is the answer to the question, what is pi plus e plus square root of 2? Well, let's all agree, first of all, that if your answer to this question is, the answer is pi plus e plus square root of 2, if that's the answer, then we can all admit, I think, that you don't really have a proper theory of arithmetic with real numbers. Your arithmetic with real numbers is really fake. In the same way that if you went into a primary school classroom and you asked the kids who've been studying rational numbers, children, what is the sum of 1/2 plus 1/3 plus 1/5? And if all that you got back was, it's 1/2 plus 1/3 plus 1/5, you know that these people don't really understand this arithmetic. Now, the fact that you can't get a better answer than this, and if you can get a better answer, then please let us know what it is. But let's make sure that we understand that I want an actually correct answer, like not a roughly correct answer. I want an exact correct answer completely, clearly, so we can all look at it and so that we can check it. Okay? And you perhaps are not able to do that, in which case I think you have to admit that the foundation of analysis, which is arithmetic with real numbers, is dubious. It's flawed. And therefore, consequently, all these theories which are built up from the arithmetic with real numbers, they are also logically compromised. Mathematics is a sort of a relentless mistress in this regard, right? If you don't have the foundations of a subject correct, if there's weakness or ambiguity or logical error in the underlying framework for a subject, then everything that you built on top of that, no matter how sophisticated, no matter how clever you are, is going to be compromised. So it's not just modern analysis, unfortunately. Also, differential geometry is largely built on real numbers. Topology is largely built on real numbers, and many other fields also. All these fields necessarily deflate once we admit to ourselves that the arithmetic with real numbers is really a kind of a fake arithmetic. And that is the reality of it. Challenge number 2, also seemingly very simple. It's just to calculate sine of 5. So the usual story is that we have functions in analysis. And The sine function is a particularly sort of elementary, simple kind of building block for a lot of other things. So sine is supposedly a function which inputs real numbers and outputs real numbers. Okay, here we're inputting just natural number 5, so it should be particularly easy. We want to compute what sine of 5 is. And when I say compute, I mean exactly, precisely, completely. It's not going to suffice, I hope you realize, just to get your calculator out and to press the sine button and the 5 button and sort of see what the calculator spits out. The calculator will spit out 8 or 16 or whatever decimals, okay? But I think we can all agree that that's not really sine of 5. That's just an approximation to sine of 5. The question is, how do you actually calculate sine of 5? And if you can't do this, ultimately, if you can't do this, then you're really not in possession of a valid theory of functions. All right? The core aspect of a function is that you input something and you actually get something out. And if you're not getting something out, or if you're only getting it out approximately, then it's not a real function. It's not a legitimate mathematical object. Of course, in applied mathematics, that's fine. We can accept that the calculator is giving us something very useful and important for practical applications. But in pure mathematics, we want to have exact theories. And so this question of whether we can compute this exactly is very pertinent. Now, there's nothing special about sine. I could have used log, tan, the gamma function, the zeta function, arc, cosine. Oh, not the gamma function for an integer, but the gamma function for some non-integer value. The zeta function, arc, cosine, hundreds of other functions. It's all the same story pretty well. Okay? Almost none of these things can, in general, be calculated exactly in terms of inputs and outputs. And so our whole understanding that modern mathematics is largely built on functions really is highly questionable. Okay? And if you watch the algebraic calculus course, especially the algebraic calculus 2 lectures, and if you've been watching some of my series in the Wild Egg Maths exploratory videos where I talk about orthogonal polynomials and power series and Pauli series, you'll see that there are legitimate alternatives to this functional fixation that we currently have that have been developed by the combinatorialists. Okay, so there's an alternative to this story, and we should really be looking at it very seriously. So that's challenge number 2. Please tell us, what exactly is sine of 5? Our third challenge, to exhibit an interesting infinite topological space. When I say interesting, I mean one that's sort of not just sort of trivial. So in 20th century mathematics, this subject of topology, perhaps initiated in the later part of the 19th century by Poincaré, more or less, emerged as quite an important discipline. And at the heart of it is this idea of a topological space, which tries to embody somehow our intuitive notion of continuity. If you've watched my famous math problem number 19, you'll know that this problem of continuity is really an absolutely fundamental core problem in mathematics, to try to model what we really mean by the continuum. So the 20th century has come up with this notion of a topological space, which these days is accepted almost universally as sort of the de facto way of proceeding in this direction. But actually it's highly problematic. And so let me illustrate that by sort of explaining, at least illustrating what a finite topological space is, to give you the main ingredients. Okay, so a finite topological space consists of a set. In this case, a set of numbers 1, 2, 3, 4, and 5. So it's just a finite set, 5 things. And then the essence of it is a set of so-called open sets. So what we're going to be looking at is some subsets of our set S. Okay, so here are a bunch of subsets of this set S. There's a subset, it's the empty set. Here's a subset just consisting of this element 1. Here's a subset consisting of 2 and 5, etc. So this collection of subsets has some important properties that characterize what are called open sets. Okay, so what are these properties? Well, the properties are that if you take the union of any two of these, you're going to get another one in this collection. So if you take the union of this set and this set, you're going to get the set 1, 2, 5, and that should be somewhere. Oh, there it is there. Okay, so the union of these two is there. Take the union of these two, 2, 5, 2, 3, 4. You take the union, you're going to get 2, 3, 4, 5, which should be somewhere. There it is there. Okay, etc. And also, this should be closed under intersections. So if you look at the intersection of any two sets in this list, it should also be there. So for example, the intersection of this set and this set, the things that are common to both, just the element 2, so there it is there. That's the intersection of these two. If you take the intersection of this one and say this one, well, it's just this one itself. If you take the intersection of 2 and 1, it doesn't have any intersection, so that's the empty set. Okay, so this is an example of a finite topological space. And it's, not that onerous because we have a relatively small number of elements sort of at the base of things. Now, the theory of finite topological spaces is not particularly developed. People don't pay that much attention to it because if the set gets big, okay, the amount of data required to list open sets in general and to check that unions and intersections are always closed, that's a lot of work. And so this is curiously a theory which almost is invisible at the finite level, okay? But nevertheless, it's this theory, when we jack it up to so-called infinite sets, which forms the basis for our modern understanding of continuity. So the challenge is to show in an explicit fashion like this, to show us a single non-trivial example of an infinite topological space. Now I have to say that in that case, for various reasons, there's a little bit of a sort of extra requirements that are required here. So for an infinite topological space, the requirement is that we should be able to take unions not just of two things or a finite number of things, but we should be able to take unions of infinite number of things. So in the usual imagination, you imagine an infinite set, okay, and then you have these subsets consisting of the open sets, and there's typically an infinite number of them, okay? So an infinite number of infinite, well, most of the subsets, not all of them, but a lot of them will be infinite themselves, okay? So you've got this huge class or set of subsets of this infinite set that you're starting with. And then you have to check these various union and intersection conditions. But the union condition is a little bit bigger. It's requiring that arbitrary unions, even if you take the union of an infinite number of open sets, you're still going to get an open set. So to actually exhibit something like this and to check that you really have a viable system of open sets is, in my view, simply something that's far beyond our capabilities, right? In reality, we're not able to exhibit such a thing, but I'm willing to be proven wrong. Okay, so I'm willing for someone to come along and in a real honest fashion to exhibit a single interesting infinite topological space. Our fourth challenge directly challenges a fundamental belief shared by almost all pure mathematicians. And that's in a result called the fundamental dream of algebra. The fundamental theorem of algebra. Okay, so the challenge is to factor this polynomial, x to the 7 minus 2x plus 3, into real linear and quadratic factors. I've pretty well just made this thing up, okay? And I'm confident that you're not going to be able to do this, but I could be wrong, okay? So that's the challenge. According to the fundamental theorem of algebra, any such polynomial factors into linear and quadratic factors, despite all the evidence to the contrary. If you actually write down some polynomial, unless you've chosen a very special one, typically of low degree, you're going to find that it doesn't factor into linear and quadratic factors. This is a remarkable situation that we've got this very direct theorem, which is sort of obviously wrong, okay? In that you just give us some random example and you're not able to do what the theorem claims that you can do. And when I say factoring it, I mean like an honest factorization. Okay, so that you actually have factors. A linear factor means something of the form a plus bx, where a and b are numbers. Quadratic factor means something of the form a plus bx plus cx squared, where a, b, and c are numbers. Okay, so you have to cook up these linear and quadratic factors, and then I'm going to multiply them all together, okay, to check that at the end of that, you're going to get x to the 7 minus 2x plus 3. And I claim you're not going to be able to do it. In direct opposition to this fundamental claim that lies at the heart of a lot of modern pure mathematics. So it's a pretty interesting sociological question how such a state of affairs can go on, and how like the entire academy just willfully refuses to even look in this direction. We just repeat this. Everybody repeat, the fundamental theorem of algebra is true. The fundamental theorem of algebra is true. All evidence to the contrary disregarded. Once you accept this or see it, well, then you realize that a lot of modern algebra, and indeed geometry, sort of deflates. It doesn't disappear. In fact, none of these subjects disappear. It's just that the results are not really true. The results are just in the form of preliminary thinking, okay? They are sort of waiting to be resurrected, taken out of the recycling bin, and analyzed more carefully, more precisely, and given more solid foundations. Huge amount of work for the next generation of pure mathematicians. Okay, so there's just so much to do here once you realize the true state of affairs. And so for our fifth and final challenge, we're going to move sort of to algebra, algebraic geometry, which on the face of it might seem to be a very down-to-earth field, but it's not. So the challenge is to exhibit even one non-trivial infinite variety. So variety over the real numbers or the complex numbers, with not just a single point in there or something. Okay. So what is a variety? Well, a variety is a set of points, typically in some linear space or maybe a projective space, but let's just stick to the linear case. So maybe a triple of complex numbers, x, y, z, such that the x, y, and z coordinates satisfy, say, an equation like this. X squared times y to the 7 plus y cubed plus 2 x to the 4th z to the 5th equals 7. So you look at the set of all complex numbers of this kind that satisfy this equation. Now, according to the usual story, this is an infinite set because, well, you can basically just assign random values to any two of them, okay? Like you can assign a random value to x and to z, and then you get a cubic equation in y. And according to the fundamental theorem, this cubic equation will always have zeros. And so you'll be able to find triples that extend the given values that you've plugged in for x and z. So from that point of view, there's always an infinite number of elements in this set, and that's then the variety. So my challenge is to exhibit such a thing. Now, if you're in algebraic geometry, you'll say, well, wait a minute, isn't this an exhibition of it? I mean, isn't this the variety? And I want to emphasize that, no, that's not. Okay? The definition of a variety is not as a string of things that evoke something. It's actually the set itself. So this is to be thought of as a description of a set. So this is not a variety, this is just a description of a variety. To actually calculate the corresponding variety, you actually have to do a lot of work. You have to actually find these triples that satisfy this equation. And unfortunately, not just 10 or 20 of them, you're obliged to find all of them. Okay, you're obliged to find all of them. So I want to just really emphasize the difference here between this description and actually finding the object. Suppose that your company, you're working for a census company, and you've just been hired by the government to perform a census and to get a list of all names of all people who are in New South Wales, Australia, on June 1st of some year. Okay, maybe next year. Okay, so your company's going to have to do a lot of work. You're going to have to go out there and you're going to have to find out who all the people are, and you're going to make a list of all the names. But you are just a recently graduated pure mathematician. So at the meeting of this team, you stick up your hand and you say, hey, I've got a good idea. Why don't we just define P to be the set of all names of all the people in New South Wales? And okay, so people say, okay, we can do that. And then you say, okay, then we're done, right? That's what we want. We want P. P is the set of all names of all people in New South Wales. So there it is. That is the set. Well, if you tried to do this in real life, of course, you would be laughed at immediately. Right? That's not the set. That's a description of the set. That's an indication of where we want to go. But there's still a lot of legwork to be done before we actually get that list of names. And it's very similar here with this variety story. This is just a description, okay? The challenge is to find an example. Doesn't have to be this one. Make up some other one where you can actually exhibit all the elements of this variety. And if you can't do that, well, then algebraic geometry deflates, doesn't it? So I actually could come up with quite a few more such problems and challenges, and maybe in some future video I will already do that. But I would like to really encourage mathematicians who are out there to actually meet these challenges. Like step up to the plate, grab the bat, and have a swing. Tell us how you actually meet these challenges. Suppose that something important depended on it. I'm J Wildberger. Thanks for listening.